now that we're moving into chapter 13, we're going to use similar computational ideas that we did in chapter 11, but in a sense we're going to take it one step further. So now basically what we're going to do is we're going to look at the way that sampling information compares to population information. So it's a lot more common to use sample data to make predictions about populations. In chapter 11, what we had was population data, and we were looking at that to make predictions about sample data values. So what we'll look at least in this video, in the beginning part of chapter 13, is just how we can make those connections and also the theory behind why it's true. So usually when I teach this class, the hardest part for people to understand is just the reasoning and kind of the theory behind it. From there, there's just a really slight adjustment that you have to make in your computations. Other than that, when we actually go through to calculate probabilities, it'll be very similar in the fact that we're going to use the normal distribution values, so the table that we used, and then finish our calculations throughout there. So I'm just going to kind of go through a set of notes on this. The first part of this video will basically describe kind of the theory, the idea behind what's going on, and then in future videos we'll look at specific computations and examples of how to actually use and apply this theorem to computations. Okay, so first I just want us to recall that the population is the entire group of individuals in which we are interested in. Okay, so the population, okay, is the entire group of people that we're interested in. So usually when we do research, we're like, okay, I want to collect this data, I want to make descriptions about some population. The difficult part of this is that they usually can't assess them directly. So let's say you want to describe every college student in the United States. Well, you are going to have a really hard time collecting data from every single college student in the entire country. So what do we do to solve this? We get samples and we'll get more notation and vocabulary for that. Okay, but either way, if we're looking at a population, when we collect data for a population, it's called a parameter. So a parameter, okay, is a number summarizing the population. Parameters are usually unknown for the populations because typically we don't collect that data for an entire population. So basically what I just said, okay, all in word stuff. All right, or typed out words, I should say. Okay, what's more realistic and what we've talked about as being more realistic is collecting a sample. So it's a lot more realistic to collect sample data. So now let's say we want to describe an entire population of college students. Well, it's a lot more realistic to gather sample data. So maybe to go to a few or various colleges, collect data from students in those colleges, make sure that they have, demographics, so there's a diverse amount of demographics, so on and so forth. But it's a lot more realistic to collect sample data than it is to get data for that entire population of college students. Okay, so let's recall that from before. We've talked about this. What the sample is. So recall the sample, okay, is a part of the population we actually examine and for which data we do have. Okay, so if you think back to kind of the beginning part of the class, we did talk about gathering samples and we did some calculations with sample data. So we had, a sample of numbers and we used our calculators to find the mean and to find the standard deviation, and we also did the 5-number summary. Well, now we're on to that kind of mean and standard deviation part. Okay, so when we did this, what we were really looking at is statistics. So here, a statistic, okay, is a number summarizing a sample. So statistics summarize a sample, whereas a parameter summarizes a population. Okay, so a statistic is the number summarizing a sample. Okay, we often use the statistics to make predictions about the unknown population parameters. So let's say we have, a bunch of data values. We know we can take those data values and collect the mean, and we've done this with sample data before in this class. Even I think it was, chapter 2 maybe. But anyway, we can use this to make estimations about that unknown population parameter. So we don't know the entire population information. Okay, so what we can do when we're doing this is find what we call a sampling distribution. So we can find what we call a sampling distribution. Okay, here, sampling distribution. Okay, So the sampling distribution of a statistic is the probability distribution of that statistic for samples of a given size n taken from a given population. Okay, so basically what's going on with the sampling distribution, and we will look at kind of a visual of this, is we take some sample, so we have a bunch of numbers over here that we've taken. Well, now from this sample, I'm going to grab a group of 4, and I'm going to plot it over here. I'm going to grab another group of 4, take that data, plot it on a graph. Grab another group, take the data, plot it. So what we're looking at there is the sampling distribution of a statistic. So you're taking the statistic, making a sampling distribution based on that. Okay. So in basic terms, different random samples taken from the same population will give different statistics, but there is a predictable pattern in the long run. So what's going on is maybe if I have this big group of data and I take a sample of 4 and find the average of that sample, and then I take another sample of 4 and find the average of that sample. Take another, find the average of that sample. We know that the averages of those 4 separate groups may be different, but in the long run, if I keep doing this over and over and over and over again, we'll find that eventually it all balances out to be the same. A more basic example of this is if you think about flipping a coin, heads or tails. We know that maybe if we flip that coin 10 times, we're not going to get perfect split of 50-50. However, in general, if I asked you right now, you'd say, oh, I'd say if I flip a coin, I know my sample space is heads or tails. What's the probability of getting heads? And you'd tell me, oh, 50% or 1/2. Okay, that's because in the long run, that's what we would expect to happen. And sort of the same idea for this, but a little bit more complicated. Okay, so to sort of illustrate this idea of what's going on, I know it's a little bit abstract and hard to understand with me just saying it, no words. What I'm going to do is just click on or go to the link that I put on the home page of Canvas so you can kind of see the visual of how this works out. So I'm going to switch this and then we're going to look at just a visualization of this. Usually in class, what I do for this is something called a penny activity, so I just hand out a bunch of pennies, so a huge thing of pennies, and then everybody takes the years on those. And then they find the average of the years they have, and then each person plots it, and we find that it creates a normal distribution. This is the same type of thing, it's just all done electronically for us. So online stat book is pretty cool. For some reason the computers here don't play the program the way that it's supposed to, so I'm just going to use the Khan Academy piece that I showed you guys, but we'll play this and I'll kind of explain what he's talking about as he moves throughout.
Really helps you to visualize what a sampling distribution of the sample mean is. So I can literally create my own custom distribution here. So let me make something kind of crazy. So you could do this in theory with a discrete or a continuous probability density function. But what they have here is we can take on one of 32 values, and I'm just going to set the different probabilities of getting any of those 32 values. So clearly this right here is not a normal distribution. It looks a little bit bimodal, but it doesn't have the long tails. But what I want to do is first just use the simulation to understand, or to better understand, what the sampling distribution is all about. So what I'm going to do is, we'll start with 5 at a time. So my sample size is going to be 5. And so when I click animated, what it's going to do is going to take 5 samples from this probability distribution function. It's going to take 5 samples, and you're going to see them when I click animated. It's going to average them and plot the average down here. And then I'm going to click it again, it's going to do it again. So there you go. Got 5 samples from there, it averaged them, and it hit there. But what did I just do? I clicked, oh, I wanted to clear that. Let me make this bottom one done. So let me do that over again. So I'm going to take 5 at a time. So I took 5 samples from up here, and then I took its mean and plotted the mean there. Let me do it again. 5 samples from this probability distribution function, plotted it right there. I could keep doing it, it'll take some time, but as you can see, I plotted it right there. Now, I could do this 1,000 times, it's going to take forever. Let's say I just wanted to do it 1,000 times. So it's this program, just to be clear, it's actually generating the random numbers. This isn't like a rigged program. It's actually going to generate the random numbers according to this probability distribution function. It's going to take 5 at a time, find their means, and plot the means. So if I put 10,000, it's going to do that 10,000 times. So it's going to take 5 numbers from here 10,000 times and find their means 10,000 times, and then plot the 10,000 means here. So let's do that. So there you go. Notice it's already looking a lot like a normal distribution. And like I said, the original mean of my crazy distribution here was 14.45. And the mean of, after doing 10,000 samples or 10,000 trials, my mean here is 14.42, so I'm already getting pretty close to the mean there. My standard deviation, you might notice, is less than that. We'll talk about that in a future video. And the skew and kurtosis, these are
Okay, so this is really all we needed to see, and then I'll kind of continue with the rest of this instead of having him go through things and explain them. But basically what's happening is if we look at this distribution up here, I think that we would all agree that's definitely not normal. Like a normal distribution is just a bell curve. So this crazy looking distribution, what he was doing in this part is saying, okay, I'm going to pull 5 samples out of here. I'm just going to pull 5 pieces out of here. 1, 2, 3, 4, 5. Okay, then he averaged them. When he averaged them, he planted the average right here. And he's like, all right, well, let's do this over and over and over and over and over again, aka in the long run. So he takes more. Does it again and again and again, keeps plotting, plotting, plotting. We can see as he does this and keeps plotting, this is turned into a normal distribution. So we can see, oh wait, this is really, really close to normal, right? I could draw a line over this, it would look like a bell curve. Then we want to notice a couple of things with that. When I do this a bunch of times in the long run, we see that the mean, so this is 14.45, this is 14.42, is almost exactly the same. What this ends up telling us, and there's a big, huge theorem that illustrates this, and I'll talk about it, it's called the central limit theorem, but basically what this tells us is, I can use this to make predictions about the population. So I know that in theory, my population mean should be approximately the same as my sample mean, which should be approximately the same as the sampling distribution of the sample means. Since all of those things should, in theory, be about the same, we can use them to make predictions about one another. So that's getting at this idea. The second thing to notice is that my standard deviation up here with my crazy distribution is really big. We can see the data is really far spread, creating a big standard deviation. But down here, we can see, you know what, this data is tucked in a little bit more. My standard deviation is smaller. So this ends up being true for any type of distribution, which really is amazing. The reason it's so important for us to work with a normal distribution is because no matter where we start, if we use this process, we can get down to that normal curve, that normal distribution, and then use it for applications. So what I'll do in the next video is basically take this entire idea, give it, you know, a name, central limit theorem, or tell us how it kind of corresponds with the central limit theorem, and then we're going to use that idea to make computations similar but slightly different than what we did in chapter 11.